In the last presentation, we looked at property diagrams, such as PV and TV diagrams. These diagrams show some of the states of pure substances, such as compressed liquid, saturated liquid vapor mixture, and superheated vapor. Remember that our goal is to be able to determine the properties of pure substances in any given state so that we can use those properties in the energy equation. The properties of a given substance can be found in property tables. There are separate tables for each of the three regions shown here. We will learn how to determine what state or region a substance is in and how to look up the properties in the tables. To demonstrate the use of the property tables, we will use water as our substance throughout this presentation. Note that similar property tables can be found for many pure substances and are used in the same manner. We will start by looking at the property table for the saturated liquid vapor mixture region. We can look up the properties as a function of temperature. For a given temperature, the table shows the saturation pressure, or the pressure at which vaporization will occur at that temperature. It also shows the specific volume of a saturated liquid at the given temperature, Vf, and the specific volume of the saturated vapor at the given temperature, Vg. Each of these properties is shown for discrete temperature values over the saturated liquid vapor mixture region. Let's look at some examples of how we can use this table to determine which region on the diagram a given substance is in. Suppose we have water at a temperature of 105 degrees Celsius and a pressure of 200 kilopascals. We know that it must lie somewhere along this line. From the table, we see that the saturation pressure at the given temperature is 120.9 kilopascals. Recall that on a TV diagram, constant pressure lines have the following form. Because the given pressure is greater than the saturation pressure, it must lie on a higher constant pressure line. Therefore, we can conclude that it's a compressed liquid. We cannot use the saturated mixture table to determine the properties. We must use a compressed liquid table, which we will discuss later. Now suppose that the temperature is the same, but the pressure is 100 kilopascals. The pressure is less than the saturation pressure at the given temperature, and so it lies on a lower constant pressure line. And we can conclude that it's a superheated vapor. Again, we cannot use the mixture table to determine the properties. We must use a superheated vapor table, which we will also discuss later. Now suppose that we know the temperature and the specific volume. If the specific volume is less than that of a saturated liquid at the given temperature, then it lies to the left of the saturated liquid line, in the compressed liquid region. Similarly, if the specific volume is greater than that of a saturated vapor at the given temperature, then it lies to the right of the saturated vapor line in the superheated vapor region. If the specific volume is anywhere in between that of a saturated liquid and a saturated vapor, then we know that it's a saturated liquid vapor mixture and that it's at the saturation pressure. Recall that a saturated liquid vapor mixture has some quality, which is defined as the ratio of the mass of the vapor to the total mass of the mixture. So a saturated liquid has a quality of 0, while a saturated vapor has a quality of 1. We will now take a closer look at the quality of a saturated liquid vapor mixture and derive an equation that we can use to calculate the quality. Suppose there is a saturated liquid vapor mixture enclosed in a container. The volume of the vapor is Vg and the volume of the liquid is Vf. The total volume of the mixture is the sum of these two volumes. Remember that the specific volume is defined as the volume over the mass. So the volume of the vapor can be expressed as the mass of the vapor, mg, times the specific volume of the vapor. Similarly, the volume of the liquid can be expressed as the mass of the liquid, mf, times the specific volume of the liquid. and the total volume of the mixture can be expressed as the total mass of the mixture times some average specific volume of the liquid-vapor mixture. Noting that the total mass of the mixture is simply the sum of the mass of the liquid and the mass of the vapor, we can replace the mass of the liquid in our equation with the mass of the vapor subtracted from the total mass. This equation can be rearranged as follows. We then divide both sides by the total mass of the mixture. We recognize now that the mass of the vapor over the total mass is, by definition, equal to the quality of the mixture. Finally, we define the property VFG as the specific volume of the vapor minus the specific volume of the liquid. If the quality of the mixture is known, we can use this equation along with the values of Vf and Vg found in the saturated mixture table to determine the average specific volume of the mixture. Or, if the average specific volume of the mixture is known, we can rewrite the equation in the following form to determine the quality of the mixture. Now let's go back to our original example where we concluded that water at the given state was a compressed liquid. The properties of compressed liquids can be found in the compressed liquid tables, where they are given at discrete temperature and pressure values. In the absence of appropriate compressed liquid data, a general approximation is to treat the compressed liquid as a saturated liquid at the given temperature. Properties of superheated vapors can be found in the superheated vapor tables, where they are given at discrete temperature and pressure values. In addition to the specific volume data, the saturated mixture tables also include data for the specific internal energy and for the specific enthalpy. For convenience, values of the difference between the specific internal energy of a saturated vapor and a saturated liquid are also provided in the tables. This property is also given for specific enthalpy. The same relationship that we developed for the average specific volume of a liquid-vapor mixture and its quality can also be applied to specific internal energy and specific enthalpy. The compressed liquid tables and the superheated vapor tables also include data for specific internal energy and specific enthalpy of the substance. For a given substance, properties of saturated liquid-vapor mixtures are also given in a separate table as a function of the pressure. It's important to note that values of internal energy and enthalpy cannot be measured directly. They are determined from relationships between other measurable thermodynamic properties. These relationships provide values for the changes in properties and not for the properties at a specified state. Therefore, a convenient reference state is chosen where the internal energy and enthalpy are assigned values of 0. The values in the tables represent changes in properties from this reference state.